Hello, and welcome to the Consulting Specifying Engineer webcast, Designing Microgrids and Microgrid Controls for Small and Medium Sites, sponsored by Schneider Electric. I'm your moderator, Amara Razgis, and I'm happy to join you today on behalf of Consulting Specifying Engineer and CFE Media and Technology. Here are some tips to help you get the most from today's webcast event. If you're experiencing any issues with your slides or with the audio, refresh your browser or click on the Refresh Media button directly under the presenter's photo. You can control the volume of this webcast by adjusting the volume on your own computer or by adjusting the volume on the webcast platform. If you're having technical problems with your audio or with the slides, click on the question mark at the top right corner of your screen to access a list of system checks to try before contacting an online technician. If you do need a technician, type a message in the Ask a Question box and someone will get to you as quickly as possible. Individual technical questions will be answered in the Answered Questions box. Type questions for our speaker today in the Ask a Question box on the left side of your screen. The live Q&A session will begin when the presentation ends in about 45 minutes. Today's webcast is being recorded and you'll receive an email with a link to the on-demand event in about a week. To download a certificate of completion or a PDF copy of this presentation, please use the Event Resources tab on the left side of your screen. Those documents are available with the on-demand version of this event too. I'm excited to introduce today's presenter, Ram Kaushik. Ram has 25 years experience in technical and business roles in engineering, IT, and software development. He is currently U.S. Offer Manager at Schneider Electric's Digital Power Division and manages strategic marketing direction for energy and power reliability management offers within Schneider Electric's EcoStruxure Power software suite. He manages a portfolio of hardware, software, and services targeted toward industrial and commercial facilities, data centers, and healthcare. He presents frequently at seminars, industry forums, webcasts, and technology panels. Thanks for joining us today, Ram. Let's get started.
It's a pleasure to be here. Thank you, Amara, for the opportunity to present to this audience on microgrid technologies. This is an exciting area of development today for a number of reasons we will get into. Firstly, before we get into the main topic of the presentation, let's see how we actually define a microgrid. So if you look at the Department of Energy's formal definition of a microgrid, it's a group of interconnected loads and distributed energy resources within a control framework. And the boundary of those distributed energy resources could be very disparate. It could be solar, it could be battery energy storage. In theory, it could just be emergency generators, right? So it's a mix of energy sources and controlled loads that enable this to operate in either island mode or in grid-connected mode. So you can see that the definition is fairly flexible, right? But in today's world, practically speaking, there is always some element of renewable resources or non-traditional energy sources in the control framework. Okay, so what I'm going to try to cover today, this is a very, very wide subject. So I'm going to make sure I hit at least the highlights in these areas. We look at some market drivers that are really fueling the adoption of microgrids at a scale which probably has never happened in the past. I'll try to classify microgrids in very broad categories. We'll look at some codes and standards that pertain to microgrids. Again, this is a very vast landscape, and I will not be able to cover these standards in great detail, but hopefully at least point out some highlights. Definitely design and specification considerations are paramount in this microgrid space, especially since the technologies are changing so rapidly. The more interesting section on use cases will be for this audience to understand that the kind of operating scenarios that are relevant in microgrids today comprise a wide variety, right, of use cases for resilience as well as economic optimization. We look at the main components of a microgrid, and we look at this emerging area called, I'm coining the term pre-engineered microgrids, but the idea is there is some canned engineering that can be done to make the deployment much smoother and recipe-based. We look at some aspects of ongoing microgrid operation and then some example implementations, which we have done in the last couple of years. Okay, let's look at the market drivers fueling the rise of microgrids. There's really three main market drivers. The first is resilience. Anybody in Texas who's lived through the last 6 months and maybe the wildfires of California can relate that resilience is really a prime driver of microgrids, because you really cannot rely on the utility being there through all these disaster scenarios. The other area is this concept of safe havens, which could be run by smart city forums or municipal governments. The idea is, of course, during disaster, you want disaster safe havens for the population. So resilience is one main driver. We'll unpack these three drivers in a little more detail. The second one is the economics of flexibly allocating where your energy comes from. The economics has changed dramatically. We now have energy as a service companies, which have, which give you energy contracts for predictable costs. So the entire economics of microgrids has changed beyond recognition. So that is fueling a lot of energy in the space. And last but not least, sustainability, right? So more companies are jumping on the net zero or carbon emission targets. So sustainability is the third major market driver. Okay, resilience. If you look at the reliability of electric utility coverage, I don't think there should be any dispute that the power grid is really getting a little more unreliable than before. Many reasons behind this. It's not that utilities are doing necessarily a worse job. It's just that they're having to deal with a lot more natural disasters and other considerations. Okay, so ERCOT was, like I said, I gave you the Texas example. A lot of customers in that area are now rethinking distributed energy resources and resilience during outages. Economics of battery storage and the solar PV installed pricing has really become, it's become a lot more attractive. And certainly there's, with electric vehicles and other such technologies, the battery storage arena has, again, it's literally a revolution going on right now. Sustainability, again, we see a lot of global Fortune 500 companies, for example, latching on to fixed carbon targets, and the way you achieve it is, of course, through renewable energy sources. So there's a lot of I give the example of Kaiser Permanente here. healthcare, industrials, and other big corporates are latching on to the sustainability story, which also drives microgrid business. Okay, so that's sort of a brief view of the market drivers that are fueling the rise of microgrids. Let's quickly look at a couple of different types of microgrids. So I would classify type 1 as this large campus microgrid. So this could be a military base. We've seen examples of universities. These days, these mega healthcare complexes are a good candidate. And of course, municipalities and smart cities. Microgrids of this type have very specialized requirements, right? So they have different types of DERs. They may have CHP in the mix. They will certainly have some custom controls. And the economic scheduling of these various resources is not a trivial task, right? So it's almost a given that anything in this large campus microgrid space is custom engineered, right? So that's what I would call type 1. Type 2 would be what I call a small to medium, which could be supermarkets, retail, could be a college or a school, pretty much anything in this, roughly less than 1 megawatt range, right? Now, these microgrids are a little more predictable, and you can define the use cases a lot tighter. And today's presentation, I'm going to be focusing mostly on this category of microgrids, because I want to talk to you about packaging these use cases. And our view from Schneider Electric is we must package these use cases in a very focused way so that we can deploy these effectively. If we are custom engineering every one of these, it is not conducive to speed and predictability, right? Okay, so with those two types of microgrids, let me jump into some pertinent codes and standards. Again, the number of codes and standards that pertain to microgrids is too vast to cover, but I just want to hit a few highlights. If you look at the sort of IEEE-based standards, there is a 1547 standard, which establishes some criteria for connecting distributed energy resources. This standard has been around for a while. It has gone through a few iterations, which I'll talk about in a minute. UL 1741 is a standard for inverters for use with distributed energy resources, another pretty important standard. We have some UL standards, 891, 1558 have been around for a while for switchboards and switchgear, but they are now, you have to interpret those standards with connections to a wide variety of distributed energy resources today. If you're dealing with healthcare, the NFPA 99 traditionally covers aspects of emergency power systems. Usually that in the past, that has meant generators and automated testing of generators and resilience associated with that. In the new era, that means healthcare in the context of a wide variety of energy assets. Could be battery storage. A lot of hospitals have PV, EV chargers, right? So the landscape has changed significantly, even in the healthcare space. There's some evolving standards. 3001 is another evolving standard. So again, there's also local standards, state level. California, for example, has its own. New York, New Jersey, there's some regional standards that are being adopted. So associated with this microgrid space, there's just a huge variety of standards we have to deal with. Okay, let's do a small, let's hit some highlights of, say, the IEEE 1547 standard. If you look at the latest standard, what it is it's a technical standard that addresses the common point of common coupling with the DER. It's technology neutral, right? And the thing to note is it has very little language associated with actual design. It doesn't prescribe what functions will be in the microgrid. So, for example, if you want to use your microgrid for economic optimization, it doesn't necessarily give you any prescriptive guidelines on how to do that, right? So it does address some scope with microgrids, but there is a scope for a lot of creativity in how you apply the standard from the implementation standpoint. Okay, a note on the evolution of 1547. It's very interesting to note, right? If you look at the 2003 language, you will see wording like shall not actively regulate voltage. By the time 2014 came around, the language said may actively regulate voltage, which means there was recognition that these variety of DERs are not there to hurt the grid, but they can supplement the grid, right? Before there was outright hostility. What shall we say? Can we call it reluctant acceptance? And by the time 2018 rolled around, the language says shall be capable of actively regulating voltage, which means it's almost a very tacit recognition of distributed energy resources as first-class citizens, right? So it's very interesting to see the evolution of the standard. Okay, so like I said, there's a lot of detail in standards that we could go through, but I want to make sure I hit the design and specification area, and also importantly, the use cases that customers are looking for. Okay, so let's attack some of these specification considerations. So a lot of customers we have seen, for a slightly more complex microgrid, it makes sense to do an assessment or a feasibility study, which accomplishes a lot of things. I'll point out a few highlights here. Identifying kind of the interconnection points, assessing the existing infrastructure, breaker nameplates, things like that, to see if there's any upgrades needed. There's also, you have to kind of formalize what your intent is for resilience. You know, how much your ride through is short and long term, how much uptime do you need, those kinds of, that's kind of a consultative assessment with the customer, and depends on, how much infrastructure you have in place and how much you want to put in, right? There's also aspects of harmonics and power quality, which come into play when you suddenly move to a distributed energy system, which have, battery, the electronics is different from say a generator. So it just introduces some transient response characteristics which bear some analysis. Now, sequence of operations, we have found from experience that this is very critical. Actually listing out the desired sequence of operations for switching loads and DERs. And finally, payback calculations for energy optimization. So there's a lot of things that can be accomplished with a feasibility study. Okay, so what are some of the design considerations that when we design a microgrid project, what do we look at, right? Choice of DERs, greenfield, brownfield scenarios, transition type, open versus closed between sources, how much speed of transition do you need, and the priorities of loads. So these are sort of just a very broad sweep on, and answers to these questions will determine how complex your controls are going to be. Okay, so I have just a few examples here to show you how these design criteria could play out, right? So different combinations of ATSs and battery, solar PV, etc., and how these critical loads, essential loads, non-essential loads partitioning, how you break that apart is going to be key to designing your microgrid system. In a brownfield installation, right, you may have existing generator ATSs that you have to integrate with. So you might have to add electrical infrastructure that interfaces with your traditional gear. Okay, so that's another electrical architectures are going to change based on that. Okay, so if you look at the UL 1741 or the IEEE 1547 wording, there's wording which says, in the event of a power failure, any independent inverters attached to the grid need to be disconnected, right? So the immediate implication, we get a lot of questions around this, which is, okay, that means the DERs are essentially disconnected and are not going to be available for use. The answer is no. It does not apply when the utility main breaker is open. That disconnection clause doesn't really apply, right? So if the facility is islanded completely, then you can certainly use your existing energy resources, battery, PV, what have you, as an anchor resource to keep your facility powered and resilient. Okay, so sort of the islanding requirement is addressed by that. Okay, one more example. So we have actually seen designs where if you, in an emergency islanded condition, the ATS will obviously be served, will switch, and the UPS will serve the critical loads, but your other loads might be stranded, right? Now, we find customers are sometimes bewildered by this, right? Because they don't necessarily understand that they have existing solar PV and battery storage, which are essentially being wasted. During a resiliency condition, when they actually need it, they're unable to use this, right? So this we've seen the stranded assets and loads problem, and this just emphasizes that your electrical design, right, matters a lot in the way these facilities are resilient or not. Okay, so let's look at a couple of examples of alternative resilient designs. Every design, of course, has its own pros and cons. If you look at this kind of a design, which is all the electrical loads are connected through this multi-source control center. We call it the Energy Control Center in Schneider, but other vendors might have something like it, but not quite the ECC. I think our ECC is fairly unique. Okay, so multi-source control center is a very nice, elegant way to do this, right? You have it's essentially an extension of what you would consider a traditional ATS, and it handles today's world of multi-source, battery, solar PV, etc. It's certainly the natural evolution. You can probably rewire it easier from an existing ATS-based design, but there are some cons, right? So you might have to reprioritize some of these loads to be wired in from the multi-source control center. Okay, so it might require, say, maybe an invasive outage to actually deploy this. Okay, so this is one alternative resilient design. We have seen this particular resilient and renewable design for healthcare facilities being touted as an option. The idea is during normal operations, in traditional hospitals, you have emergency, you have for islanding, you have emergency generator capabilities. But the DERs are not really used to optimize energy costs in a non-islanded situation, right? So let's say you're running the hospital by regular means, you might have you might have a variety of energy sources which are not being optimized for energy usage, right? So if you in this kind of a design, you can actually share the battery and PV across for both islanding and for non-islanded scenarios, right? So these are available for resilience, but when you do have an emergency, you can also run these and reduce your diesel storage capabilities, for example, right? So because diesel fuel storage has its own safety concerns, fire safety, etc., right? So if you say, okay, you've got PV capacity to run during that time, it's going to improve the situation. All right, so let's jump into some of these use cases which we are seeing quite a lot of, okay? I want to at least give you a broad sense of what these use cases fall into. So the two categories that we see are microgrid operation, so day-to-day, what you would expect a running microgrid to handle, right? So you need the capabilities for remote monitoring, you need the alarming and notification, you probably need some kind of local graphical interface. There's often some limitations on export management. Utility might have some guidelines which limit grid export. This is very common in California and the Western US, and this is a common requirement. Grid connection management, where you have to manage islanding sequences and restoration sequences, right? So when the utility comes back, you need a very logical, progressive way to add loads back, right? So this is very common in what's called load preservation systems, right, where you manage the load in a very prescribed way. It just becomes very important in a microgrid because you're also juggling different energy sources. So this grid connection management is a key feature. The ability to automatically shed and reconnect loads based on that balance. Okay, so there's a lot of use cases, and we'll look at these in some detail, but I want you to get the broad picture first. So the second category of microgrid functions are in the area of microgrid optimization. So what is optimization? What are you optimizing? Energy optimization, where you are managing PV, battery, etc., to actually take advantage of rate tariffs, right? So if you have a sunny day, your on-peak tariff is pretty high. You can ramp up your solar PV production and really reduce your electric bills. You can also look at demand charge reduction, where you can predict roughly where your peak is going to land and ramp up, say, battery storage during that period, right? So and the economics are very, very good, right, for this sort of smart microgrid management. Okay, so these two categories of use cases are paramount in microgrids today. And the thing to note is these use cases for the smaller microgrid, you can standardize these use cases and build it roughly into a productized form. And I'll show you how we have been doing this in Schneider. Okay, let's do a very broad sweep of how these functions would operate. So remote monitoring, I have some examples here. You can juggle, you can look at a view of, okay, what is the production situation today. How much is PV producing, how much is utility giving the facility, etc. And you can look at trends and sort of evaluate what is going on a day-to-day basis. Okay, so this is sort of bread and butter for regular microgrid monitoring. Alarms and notification, again, I would say this is par for the course, right? You need some detection of abnormal operating conditions. You want to track sequence of operations on islanding sequences. I mean, did things happen the way they should have? Troubleshooting, etc. Okay, so this is again standard stuff. A local HMI of some kind is again pretty much expected. You want to look at the operators locally want to see how the microgrid is operating. Export management. So PV curtailment is increasingly a scenario where the utility might have some guidelines around this. You want to protect against unintended export to utility. So this is export management is a key use case for microgrid operation. Now, I mentioned grid connection management. What I mean by that is these sorts of what can be complex on the surface, at least to look at, control sequences. So if on islanding, if you have solar PV capacity, what do you do? If you don't, what do you do, right? So there's different nodes of this state tree that have to be coded in to a control sequence. Okay, so that is also key to microgrid management. Okay, on the load side, you have to manage the sequence of load shedding and restoration. So you might have to prioritize which loads are higher, lower. You might have to set kind of delay timers. So there's features like that built into load management. Forecasting. So this is interesting, right? So sort of an emerging area where we can look at, say, even weather patterns and real-time rates, for example, and do some forecasting based on the prior load profiles of the facility. And we can have an idea what we are going to do, say, tomorrow, right? Will PV ramp up? Do we have enough battery storage to run through certain periods of the day? Okay, so this sort of forecasting features. Now this falls in the optimization. If you see the legend on the top has changed from operation to optimization. Okay. Energy optimization and demand charge reduction I've sort of clubbed together. If you look at this screenshot, you can see that in the off-peak period, we have actually charged the battery when energy is cheap, or nothing is cheap, less expensive, shall we say. Okay, so the facility has charged the battery. And then during the on-peak, you're actually using the battery, the storage, the stored energy, right? And you're avoiding using very valuable kWh from the utility. Now, the other facet is you can also do peak shaving. By optimizing the local energy sources, you can, there's two ways, right? One is you're avoiding peak demand, and the other is you're participating voluntarily in a demand response program to get some credits back from the utility, right? So both those scenarios are possible. If you look at the screenshot, you can see the on-site loads are ramping, but we are starting to use the battery and not hitting that peak. So this can also really be productive in terms of return on investment. Okay. Many facilities have some sort of a net zero, they're beginning to at least, try to be net zero over a period of time. So you can sort of charge energy storage systems using PV and then consume it later in the day. And you can sort of play this game of I call it the energy dance, right, between different energy sources, and that's a pretty valuable game to play. All right, that was a very very fast sweep through a lot of different use cases, but I wanted you guys to at least understand that there is, we are really juggling a lot through, in a modern microgrid, right? We have all these operating scenarios which manage loads and energy assets, but we also have these optimization use cases. And it's the combination of those two that really make sense in today's environment. 5 years ago, 10 years ago, you might have just one of those use cases, but now we're beginning to see all of this come together. Okay, let's look at some of the components of, say, a typical smaller microgrid. By and large, this is true of even the customized microgrid that I alluded to earlier. But like I said, I'm going to focus on the smaller size packaged microgrid. So at the lower level, you see connected assets, and these could be battery energy storage, inverters, EV chargers, generators, etc. On the control middle layer, we have sort of the brains, which is a microgrid controller, could be a sophisticated one, could be a PLC based, many number of options there, dedicated controllers, which control the switchgear, and on the communications gateway, it feeds data to an optimization engine, which then is generally cloud-based, which does the smart algorithms to actually optimize the microgrid. Okay, so these three layers are, conceptually speaking, what constitute the Schneider, what shall we say, view of how the microgrid should be controlled. By and large, I think other vendors have different, slightly different architecture, digital architectures, but it's more or less conceptually the same. Now, you can see that with all these use cases, these microgrids appear to be, gaining in complexity very quickly. You have a mix of technologies, controllers, software, electrical switchgear. You might have varied skills needed and many different use cases to consider. Some customers might need some of those use cases and others might need others, right? So at least on the surface, it looks like it's going to get complex quickly, and we're going to have custom engineer all this stuff, right? I want to tell you that that's not necessarily the case, right? So we are approaching this arena of pre-engineered microgrids, and what that is at Schneider, at least, we are moving to this idea of code generation to use automatic code generation to actually engineer these use cases. So the way, roughly, how it would work is you specify the configuration of DERs and loads first. That's kind of step one. What are the energy assets you have? How much PV? How much battery storage? Generators, etc. What's your load organization? Critical loads, non-critical loads, etc. You specify the use cases that apply. Are you interested in demand charge management? Are you interested in any other kind of export or time of use tariff, etc.? So you sort of check the use cases you apply. You can do a little bit of configuration on the parameters, depending on, like, let's say you chose one of the tariff structure optimization. Well, then you have to specify the tariff, right? So, on peak, off peak, whatever, right? And at the end of this exercise, we generate deployable code, which can be factory tested before we deploy in the field, right? So it's fairly It reduces risk for specifiers and designers. And for customers, it's a predictable microgrid which we can document way ahead of time, right? So that's this idea of pre-engineered microgrids. And for smaller, for the sort of type 2 microgrids, which I classified earlier, it really makes a lot of sense because you don't have to individually program all the components. The communications and control wiring are pre-wired at the factory. Your sequence of operations is fairly, can be documented and specified ahead of time rather than expensive on-site testing. You have the optimization use cases, and you can quantify that, right? You can look at the tariff structures and say, this is, with this particular load profile, this is what we expect in terms of return. The safety use cases are already pre-engineered. So we are kind of sold on this idea of pre-engineered. Even if we get to the 95% precision point, we find it's really a lot more efficient to deploy. Okay, so that was the idea of pre-engineered microgrids. A quick note on ongoing operation. So, once the microgrid is deployed, we still have sort of ongoing things that require allocation of a O&M budget, right? And it's important that customers and design engineers are aware of this. So there's an operational aspect of troubleshooting alarms and any kind of operational issues that crop up. You need to analyze maybe some forensics, right? What happened when? Did the PV switch on when it should have, et cetera, et cetera. There's a maintenance aspect to all the controls and the gear. And there is a financial reporting aspect where you should really audit the return of investment on the microgrid in an overall sense, right? Did your economic optimization of juggling these assets get you your return? And there could be a carbon emission aspect to this as well, right? Where you have to actually report the carbon emissions based on your mix of energy assets. So the point to take home is that there are a lot of ongoing activities associated with a microgrid. So it's, there's a CapEx spend and there's an OpEx, which is unavoidable, right? It's just a question of allocating for it. Okay, so that's sort of a view of the ongoing services. Finally, let's look at a couple of example implementations. And these are very broad examples that I'm going to show you because we've done a variety of microgrids for other applications. I mean, the government campuses, and those are sort of very different, right? So this is a farming example where it's we deployed solar PV. It also had generation. We had some partners that financed and built the microgrid. And the energy as a service idea has also been touted here, right? Where, there are companies, Schneider has a couple of joint ventures with them. There's other companies there which have an energy as a service model, which is hugely attractive to end customers, where they have a predictable cash flow on what they're going to spend in energy, and the risk is assumed by the energy as a service company. And they deploy this microgrid, and the customer just gets a predictable cash flow and predictable energy. So this is one example. Another logistics facility where resiliency was the driver. They were very keen on a 24/7 type shop with disasters hitting the area. They needed drive-through capability. So this was and they did have solar PV and batteries in the mix. Okay, so this was another logistics facility that we deployed a smaller microgrid. Another one that's in process right now is a school campus. Again, the public safety power shutoffs are the main driver here. For those not in California, these are essentially state mandates because of wildfires and other disasters, where the utility will cut power, and you could be islanded for days, right? So that changes the design paradigm even for hospitals, where it's not the traditional 72 hours of diesel gen capacity. Now you're thinking a week, and you're thinking, okay, I need to get solar PV and battery storage and other means where I can keep ride through resiliently indefinitely, right? So we're seeing more and more of these sorts of use cases driving action in microgrids. Okay, so quickly, let me just summarize what we went through, and I'll give you some main points to look at. So we looked at the market drivers fueling the rise of microgrids. There were three of them: the economics, resiliency, and sustainability. We looked at two types of microgrids: the large custom engineered microgrids and the smaller packaged microgrids, which are coming into vogue now. We took a brief tour of pertinent codes and standards. There are many. We looked at some design and specification considerations, where different kinds of designs for greenfield versus brownfield, the way you switch assets, and the way you which side of the controls you are going to drive different kinds of controls, right? We looked at operating scenarios in the microgrid operation and microgrid optimization area, right? So I took you on a brief tour of these use cases, and different customers gravitate to different combinations of these use cases. We looked briefly at this idea of pre-engineered microgrids, where the use cases are merely configured and generated automatically. Of course, you can custom engineer any possible combination of controls, right? But it gets expensive, and this is a way around that to standardize the option. We looked at what are the things to look at for ongoing microgrid operation. And then finally, I showed you a few of the sample implementations of microgrids that we have done in the recent past. Okay, let's summarize key takeaways, right? One is, like I said, the three drivers of the rise of microgrids: resilience, energy economics, and sustainability. You can evaluate which ones of these are important for your customers and your specifications, right? Whether they make sense. Roughly, the segmentation, large campus microgrids, and the small, and those power guidelines are sort of squishy, right? 50 kilowatts to 1 megawatt. That definitely squishy. Very technical term, squishy. It's good to learn that. But there's certainly some leeway there. Microgrid applications, two categories: microgrid operation and optimization. For the small microgrid market, these use cases can certainly be packaged and pre-engineered with design tools for efficient deployment. And we look forward to doing that with our customers. Okay, so that sort of concludes the presentation. I want to leave you with a few, no professor leaves an audience without some homework, right? So the homework is, you can look through some of these microgrid solutions overviews that Schneider has put out. The Energy Control Center is the sort of packaged microgrid electrical gear plus controls. and I included a small brochure on microgrid solutions for small and medium buildings. Okay, with that, Amara, I hope I am on time, and I hope I can turn it over to you now.
All right. Well, thank you, Ram. That was a ton of information in a short amount of time, so I appreciate it. And now our presenter will answer questions from the audience. Please type your questions for the presenter in the Ask a Question box on your screen. And we'll get to as many questions as time allows. Questions that we do not get to today will be posted at www.csemag.com with the archived version of this webcast. And please remember to download a certificate of completion or a copy of this presentation with the resources that Ram just referred to. Use the Event Resources tab on the left side of your screen. All right, Ram, let's get to a couple of questions here. The first one is a two-part question. When do we need a microgrid, and what are the items we need to coordinate with the utility when we design a microgrid?
Okay. So when do we need a microgrid? So I think I would refer back to those three trends, right? So depending on the customer, each one of those levers could be the turning point, right? So we have customers where, for example, the California public safety cutoffs that I alluded to is just, for them, resilience is key, right? I mean, you have facilities which are safe havens, which simply, a week with the utility cutoff is just unimaginable there, right? So that drives, addition of non-traditional energy sources, and that immediately facilitates, okay, how do we connect all this in a meaningful way and control it intelligently? So that would be, an example where the customer is kind of a small, let's say, a municipality or even a police, some kind of mission critical infrastructure that is driving the microgrid, right? So you could also have the sustainability example where there's a corporate, Procter and Gamble or one of these big corporates saying, you will achieve X amount of carbon emissions reduction, and we are going to fund, renewables in all our plants. And now that immediately facilitates the controls discussion. So it just depends on what fuels what is the match that lights the spark, right, for microgrids. So, okay, so second part of the question was, what are the discussions with the utilities that can happen? That's a good question. So we've seen discussions on interconnection points. We have seen discussions on export management. Are you allowed, should you be exporting back? Is there an opportunity for demand response programs? Let's see, what else? Solar PV curtailment. Utility might have some guidelines which you have to pertain to. You can have a discussion on tariff rates if you want to play the optimization game with the utilities. That's another point of discussion. So I would say the discussions with the utility are a very, very important facet of deploying a good microgrid. There are a lot of aspects to be covered there.
Sure, got it. Thank you. Oh, wow. This is another multi-part question, Ram, and I can come back to any of this if you need me to.
Okay.
First part, what are the key components of a microgrid system? Second, communication method between these key components. And third, how can we make readily available components in the market compatible for a microgrid?
Boy, okay. Okay, one thing at a time. So part A was, can you rephrase that one, Amara?
Yeah, so part A is what are the key components of a microgrid?
Okay, let's tackle that one first. So the key components would be the distributed energy assets. So for example, battery sources have their own controls and communication protocols today. Similarly, you have maybe generator controls if you have generators in the mix. So each energy asset has its own kind of control interface, right? So that's one portion. So I would say that's kind of the lower, if you remember the 3-layer digital architecture, that's sort of the lowest layer is your control interfaces with all your assets and your loads as well. So if you have communications methods to talk to smart breakers or whatever, right? So that falls in that lowest layer of the digital architecture. In the middle layer, you have microgrid controllers. You might have communications gateways, etc., to crunch data and push it up to some kind of optimization engine, right? So you have a controller which manages all those use cases we talked about on the microgrid operation, right? Things like, okay, I send a signal to turn on the PV. I want to, in an islanded case, I may want to actually open the main, right? Although all that intelligence is in the microgrid controller algorithms, which is in the middle layer. On the top layer, the optimization engine has to be sort of one level up in brains because it's actually orchestrating what should be done to optimize the microgrid. And it has the tariff rates, it has maybe the demand charges, it has potentially a weather forecast. If it has a forecast of bad weather coming through, it might be an opportunity to charge the battery ahead of time and be ready to ride out a possible islanding, right? So 3 layers, control layer, energy assets and breaker asset layer, sort of connected gear. Second, middle layer is the control layer, and the third layer is the optimization layer. Okay, second part of the question, Mara.
Yeah,
sorry.
Part B, you kind of answered this. What's the communication method between these layers?
Okay, so we have found this all over the map, right? We have standard communications like Modbus, and sometimes even hardwired, right? You can send generator start signals, for example, hardwired, right? In terms of cloud communications, many vendors have some, web services or some sort of software SOAP type communication protocols, REST APIs, whatnot, right? So it depends. But I think on the device layer, we can support a wide variety of protocols. Part C, Mara?
Got it. All right. And this is the last question that we have time for. So part C is, how can we make readily available components in the market compatible for a microgrid?
Yeah, so this is a difficult one. There are some industry efforts to standardize some of these, and you can actually the use cases that I said we are trying to productize are kind of a manifestation of that standardization, right? So this is a journey I think the industry has to go through. You can see the technologies are changing fast in this space, right? What was battery technology 10 years ago is unrecognizable today. So this is a journey we have to go through.
Right. So a bit of a squishy answer because so much is changing so quickly.
Absolutely. Yeah.
Got it. All right. Well, thank you. And thank you for the great questions. And Ram, I'd like to give you a very special thank you for sharing your time and expertise. I'd also like to extend a thank you to our sponsor, Schneider Electric, for sponsoring today's event. Now that we are just about done, we want to hear how we did. The exit survey will pop up on your screen as the webcast ends. Please take a moment to complete it because we do use this information to improve upon future education events. Finally, on behalf of Consulting Specifying Engineer and CFE Media and Technology, I'd like to thank you for attending. This now concludes our webcast session. Thank you and goodbye.